Okay, before we get into our next set of notes, we're going to do a little bit of review from earlier this year with degrees of our polynomial equations. So degrees focus on your exponent. Here at the top you see some notes. The degree of the polynomial is the highest exponent. We're going to add in a little bit here when you're adding or subtracting terms. Okay, we will see an example later on in our notes when we're multiplying all the terms, and we'll have to figure out the degree a little bit different. Okay, your leading coefficient then is the number, so coefficient's always a number, in front of the highest degree term. So for this first example here, our highest degree, or our highest exponent, is this 3. So degree of the polynomial is 3. And your leading coefficient, or the number in front of that term, is 2. For your second one, your highest degree is a 2. Your coefficient is 4. The last one, you have a degree of 4. There's no number written in front, so it's automatically a 1 in front of this x. And then when there's no number or exponent written above, it's automatically a 1. And then you have 8. Okay, just for example purposes, if we had an x minus 4 cubed, then let's say x plus 1. In order to find the leading coefficient of this, because they're being multiplied together, you would have to FOIL all of that out. So you would have to write x minus 4 3 times, and then x plus 1. Okay, so that's a lot of work. But as we're going to see later on, the super important thing is we're just kind of focused on the main term. So we have 4 x's here, okay, all have an exponent of 1. So that means you have the degree is going to be 4, because that's your highest value, and then your leading coefficient. If you were to multiply that x all the way out, okay, and I'm not going to do that, you can pause it and go ahead and multiply this out. There's no number in front of the x, so your leading coefficient will just be 1. So your polynomial will be something of x to the 4th plus some other number, x cubed, and so on. Okay, so you'll see some examples later on. But the main reason we need that is to figure out your horizontal asymptotes of rational functions. We looked last video at your vertical asymptote, so that's a vertical line that your graph will approach but doesn't cross. Now we're going to look at the horizontal asymptote. So there's 3 different rules that go with this. Okay, so as we're going through these slides, go ahead and pause them so you can write down the notes if you need. Horizontal asymptote is a horizontal line that the graph of a function approaches but never reaches. Okay, so just like a vertical asymptote, same thing, except now this is a horizontal dashed line. So our 3 rules. If your degree of the numerator, so remember degree is your exponent, is smaller, that's your key word here for the rule, than the degree of the denominator, then your horizontal asymptote is automatically a line y equals 0. So here you have this example. Let me go to this slide here. Of x squared plus 3 over x cubed plus 4. Okay, so you can see they're highlighted in yellow are your degrees. Your degree of your numerator is smaller. Okay, 2 is smaller than 3. So your horizontal asymptote is automatically y equals 0. That's all you would write for that. So at the line y equals 0, you have a dashed horizontal line. That's rule number 1. Rule number 2, if your numerator and denominator have the same degree, same exponent, then the horizontal asymptote is the line y equals a divided by b, okay, and that comes from your coefficients. So a and b are both coefficients. A is coefficient of the numerator, b is coefficient of the denominator. So here we have an example. Highlighted there in green, you see the degrees for both of those, numerator and denominator, is 3. So they're the same. That means we need to take the number out in front, so that's your coefficient, and we're going to divide them. So written down here in red, you have 4 divided by 2. When you simplify that, that's just going to be 2. So y equals 2 is your horizontal asymptote. That only applies when your degrees are the same. Okay, and then the last rule that we have is when your numerator is larger than the degree of the denominator, there is no horizontal asymptote. So in your example, we have x to the 4th all over x squared. Because the 4 is greater than 2, there's no horizontal asymptote for this problem. Okay, I know I went through those slides really quickly, so pause them, write down what you need for the rules. And now we're going to actually look at a few examples. So we have this example here. We're going to combine everything from kind of this unit. We're going to factor out stuff, find points of discontinuity, and then label vertical, horizontal asymptotes, holes, and we're actually going to go back to what we did in the very beginning of the year and look at our domains of function, so your x value. So first thing we want to do is we want to go ahead and factor this denominator. X minus 1 stays at the top. You're looking for numbers that multiply to a -4 and add up to a +3. Okay, so I need a 4 and a -1. So my factors become x minus 1 and x plus 4. Now before we do anything, first thing that we want to do is we want to go ahead and list your points of discontinuity. Okay, so that's anywhere in your denominator where it could equal 0. So we're going to set both of those factors equal to 0 and solve for x. So x can't equal 1 and x can't equal a -4. Okay, points of discontinuity, we can do that. Horizontal asymptote, we are going to look at your degree. Okay, so horizontal asymptote, we're looking at the degrees of your exponents. Okay, so we can actually go back here to the one in red. So that looks a little bit easier to figure out your degrees. On your numerator, you have a degree of 1 over that x, and then you have a degree of 2 as your highest degree on the denominator. Because your numerator degree is smaller than your denominator degree, your horizontal asymptote is automatically y equals 0. Okay, vertical asymptotes and holes we're going to get by canceling things out. So going back to our graph here in purple, your equation in purple, you can cancel out the x minus 1. So if we cancel that out, that means that there's a hole at x equals 1. Okay, let's keep simplifying, and then you have 1 over x plus 4. So because I cannot cancel out that 4, that's going to be my vertical asymptote. So wherever that factor is, that's an x equals -4, that's going to be your vertical asymptote. All right, and then the last piece of information that we need to do is your domain. Okay, domain is coming from your points of discontinuity. So when we write domain, we do x, because domain is your x values, such that x cannot equal, we have 2 points it can't equal, -4 and 1. Okay, so it's x is your first term, vertical line is such that x cannot equal -4, 1. So that's telling you you can have all x values except for -4 and 1. We got all of those pieces of information from the previous video this week and some from the past lessons that we've learned in Algebra 2 as well. Okay, so you will have to list all of these characteristics. It's going to be a little bit of work for this stuff, but shouldn't be too taxing for the math portion of it. Let's look at another example now. Okay, here you have this equation. You can do your horizontal asymptote from the beginning or at the end. Actually, we're going to save it for the end. It's a little bit easier to do it at the end. So we have horizontal asymptote, vertical asymptote, points of discontinuity. We have holes in our graph, and then we have our domain. Okay, because our denominator is already factored, let's go ahead and find our points of discontinuity. So we have a 2x minus 4 equals 0, and then an x plus 6 equals 0. So let's solve for x. So we have x can't equal 2 and x can't equal -6. All right, in order to keep on solving, we are going to go ahead and factor out. Okay, sorry about that. We're going to go ahead and factor our numerator, seeing what numbers multiply to -6 and add to +5? So your factors for your numerator become x plus 6 and x minus 1. Okay, now we're going to go ahead and cancel any terms that we can. So we can cancel out the factor of x plus 6. When you cancel that out, that factor then becomes a hole in your graph. So there's a hole at x equals -6. All right, let's keep solving. You have an x minus 1 over a 2x minus 4. Okay, so there's one factor that we weren't able to cancel from our denominator. So that means it's going to be a vertical asymptote where it's the 2x minus 4 factor. So that means at x equals 2 is a vertical asymptote. Now that we've simplified it, we can check our horizontal asymptote. Your degrees for your numerator and denominator are both 1, so they're the same. If they're the same, then your horizontal asymptote is your coefficients in front. So the number in front of x on your numerator is 1, and the number in front of x on your denominator is 2. So y equals 1/2 is your horizontal asymptote. Okay, we got that from your highest degree once we simplified it all. Last thing that we need to do is figure out your domain, and that comes from your points of discontinuity. So again, we have a bracket x such that x cannot equal, and we have two values, -6, 2. Okay, so your domain should all be coming from your points of discontinuity because we're dealing with values of x. All right, there's one more problem that I want to look at. So we have this one here. Okay, this is kind of going back to one of the examples I talked about at the very beginning of this slide. It's a little bit challenging to see what your degrees are going to be. So what we're actually going to do is we're going to write this all out. Because I have x plus 5 squared, that means I have 2x plus 5s. Then I have an x minus 3 cubed, so I have 3 of those now. Okay, I'm going to do the same thing on my denominator because it's going to allow me to figure out which ones can cancel. So I only have 2 of the x minus 3s and 2 of the x plus 5s. Okay, first I want to do is points of discontinuity. Okay, so I have points of discontinuity is what I'm looking at. Those are coming from your denominator. I have a couple repeated factors, so I only need to include the factor once when I'm finding the points of discontinuity. So I have an x minus 3 factor and an x plus 5 factor. I'm going to solve for x, and I get x can't equal 3 and x can't equal -5. Now that I've done that, I can go ahead and cancel out any factors. So I can cancel out 2 of my x minus 3s. Because I canceled that out, that becomes a hole at x equals 3. Okay, I only need to account for it once. I can also cancel out an x plus 5. I can cancel out both of them. So there's also a hole at x equals -5. Now I'm going to simplify. When I simplify, I'm only left with x minus 3. That's it. So because there's nothing on my denominator, there is no vertical asymptote. And my horizontal asymptote, I have x minus 3 over 1. My degree on my numerator, I have x to the power of 1. And because I don't have any x on the denominator, it's x to the power of 0. So my degree on my numerator is larger than the degree on my denominator. So that goes to rule 3. There is no horizontal asymptote either. And then all you need to do is list your domain, x, such that x cannot equal 3 or -5. Okay, x cannot equal 3 or -5. A lot of very specific points that you need to look at. Your worksheet, you did not have a worksheet for the last video, is going to have 6 problems. You're going to list all of those values. You do not need to worry about finding the range. Just focus on domain. There are going to be 6 graphs, so try your best to graph them. A vertical line, dash vertical line, where it's a vertical asymptote, and a hole at the point where you have the x value for your hole. Do your best to graph. If not, just list the characteristics.